In this lecture, I am going to talk about solutions. Solutions are highly important for any lab experiment, whether it is a molecular biology lab, biochemical, chemical, or analytical, or any lab where solutions are used. Why are these solutions so important? A solution with incorrect concentration may lead to wastage of your precious time and funding. Like, for example, you have to do a series of experiments, and in one of your earlier experiments, one of the solutions is not correctly made and you don't know about it. What will happen? Maybe after a couple of weeks or maybe in month time, you find out your experiments are not working, and when you go back and check your solution concentration, the solution concentrations were wrong. So, but by that time, you have wasted your time and funds. So, I will go through the different types of solutions, that how you can prepare those for your experiments. Here are examples of some solutions that are used in different labs, and of course the types and number of solutions is in thousands, not in hundreds. But here I give you basic theme how to prepare those solutions. Some solutions are very simple, other ones are complicated, but basic theme is the same. Like, for example, this is tris EDTA buffer. In research paper or in the methodology, you may find this statement: 10 millimolar tris chloride, 1 millimolar EDTA. But how to prepare this solution is basically an art, that how you prepare those solutions and then mix those in exact concentrations. This is what I'm going to tell you in this lecture. Solutions may be made in different formats, like molar solutions, molar, normal, percentage solutions, parts per million, parts per billion, etc. But I will concentrate more on the mole and the molar concept first, and then in the later part I will discuss something about other types of solutions as well. But in most of the molecular and biochemical labs, mole and molar concept is used, and many students, they in fact confuse this concept of mole and molar. So what is the difference between these two? Mole is basically a quantity, and simplest definition is molecular weight expressed in grams is mole, and its abbreviation is MOL dot, is the abbreviation of mole, not the molar. For example, if you want to take 1 mole of glucose, you have to take its molecular weight, which is 180. So if you take 180 grams of glucose, it contains 1 mole. Whereas if you take 40 grams of sodium hydroxide, that contains 1 mole as well. So you have to take different weights to get 1 mole of anything, and it's simply the molecular weight of anything correspond to the mole. Now, why mole? In molecular biology or even in biochemical or chemical reactions, we are dealing with molecular interactions. Therefore, we need solutions with quantity in terms of mole, because when we talk about mole, we in fact are talking about number of molecules because of the Avogadro's number. Number of units in 1 mole of any substance is this figure, 6.022 and so on, into 10 raised to power 23. So it means if you take 1 mole of glucose and 1 mole of sodium hydroxide, although they are different in their weights, but they contain same number of molecules. And the unit of Avogadro's may even be electrons, atoms, ions, or molecules. But here we are more concerned about molecules, especially when we talk about molecular biology or biochemistry lab. As I mentioned earlier, if we take 180 gram of glucose and 40 gram of sodium hydroxide, they will contain 1 mole each of the glucose and sodium hydroxide. But if we take glucose and sodium hydroxide in equal quantities in terms of grams, they will have different number of molecules. For example, if we take 80 gram of glucose, it will contain 0.44 moles. by this simple formula. How to calculate this? Like 180 gram of glucose contains 1 mole, and 1 gram of glucose will contain 1 over 180, and 80 grams will contain 1 over 180 multiplied by 80. This is simple unitary method. I will explain this unitary method more later on. But I hope you remember this from your primary school mathematics. And 80 gram of sodium hydroxide contains 2 moles. Now we can calculate the number of molecules in a mole, and I mentioned earlier as well that molecules we are interested in because of the molecular interactions. So this is the formula: N equals to capital N equals to N into Na. So this is the number of molecules, and this is the number of moles, and this is the Avogadro's number. So by applying this simple formula over these calculations, you come up with this number of molecules in glucose and this number of molecules in sodium hydroxide. Although you have taken equal grams of both, you have taken 80 grams of glucose containing this number of molecules, and 80 gram of sodium oxide containing this number of molecules. These are very much different. So if you want to take equal number of molecules, you have to take in terms of mole, not in terms of gram. Now what is molar? Molar is concentration, and it always means per liter. Like this is the abbreviation for molar, and it means moles per liter. And this is neither small nor capital, but it is small capped. And in my another lecture, I have discussed how to write units and their abbreviations correctly. For example, for glucose, 180 gram glucose per liter means 1 molar, means 1 mole of glucose per liter is 1 molar. Similarly, if you dissolve 180 milligram of glucose in 1 liter, that is 1 millimolar. And micromolar is 180 microgram of glucose dissolved per liter is 1 micromolar. So meaning that molar, wherever it comes, it always means per liter. For example, you want to make 1 molar solution of glucose. So for that we will dissolve 180 gram of glucose in a beaker with magnet placed on the magnetic stirrer in a less volume, of course, like 700 ml or so, and you dissolve it in, and then you make the final volume to 1 liter in volumetric flask. You cannot start to make making solution of 180 gram of glucose in 1 liter, because in that case the volume, final volume, will be more than 1 liter and your solution will be incorrect. So this is how you make this 1 molar solution of glucose, keeping in view of the concentration. Making solutions is not as simple as I just have mentioned, because usually we don't make solutions in high volumes. Like if you want to make 1 molar solution of glucose, you have to dissolve 180 gram of glucose in 1 liter of water. But you may not need that much volume of the solution, like 1 liter. So what we do is we usually make solutions in much less volumes. Like you may make 1 molar glucose solution just in 100 ml. So to make that, you dissolve only 18 gram of glucose in a beaker in a similar way in less volume, like 70 ml of water, and after dissolution you can make the final volume to 100 ml in volumetric flask. And remember, always use volumetric flask to make the final solutions to get correct solution concentration. So here what we have done is we just reduced the volume to 10 times, like from 1 liter to 100 ml. And similarly, you reduced all amounts in the similar way. Rather than taking 180 gram, you just have taken 18 gram. Similarly, you may need to make a solution in much lower concentration. Rather than making 1 molar, it is only 1 millimolar and 100 ml of solution. So, taking the example of glucose, in this case, you have to dissolve 18 milligram or 0.018 gram of glucose in a beaker, and with a magnetic stir in about 70 ml of water, and making the final to the 100 ml. So here what we have changed is from gram to milligram. As I mentioned earlier, to make millimolar solutions, you may take milligrams rather than gram. So it will be 1 millimolar solution. Now taking example of another solution which we usually come across in our molecular biology experiments, to just to 1 micromolar, 100 ml of 1 micromolar solution, and for if you want to make that for glucose, you have to dissolve 0.00018 gram of glucose in 100 ml, and this is very low amount. It is very difficult to, or it won't be possible in even normal analytical weighing balance. So what we do here is we make concentrated solutions and then dilute to our required concentration. So let us see how to do it. We have made concentrated solution of 1 millimolar glucose in 100 ml. As I mentioned that we dissolved 18 milligram of glucose in 100 ml to make 1 millimolar solution. Now if we want to dilute this solution to 1 micromolar, we can use this formula C1V1 equals to C2V2. So on one end, we have the solution, we have the concentration we have, and on the other end, we put the concentration which we want to make. So in order to use this formula, the units should be the same in both ends. For example, we have this 1 millimolar solution, and if you want to make 1 micromolar solution, we have to convert this millimolar to micromolars. So in fact, we want to make 1000 micromolar. It is the same thing as 1 millimolar. So we convert these to micromolars. Now, using this formula, C1 is the concentration we have, which is now 1000 micromolar, as I just calculated from here. And V1 is the volume we want to find out. And this C2 is the concentration we want to make, like we want to make 1 micromolar. And V2 is the volume we want to set, and this you can set by yourself. Like here I set 100 ml, but if you want to make it this solution to maybe 10 ml, maybe 250, 500 ml, or even 1 liter, you can set here. If you want to do it 1 liter, you have to set it 1000 ml to make the unit same on both ends. So here I set it at 100 milliliters. So when you adjust these in this formula, this C1 will be divided by C2, and V2 will go there. Simple mathematics. So V1 equals C1 C2V2. C2 is 1 micromolar which we want to make, and 100 ml which we want to make the solution is V2, divided by C1, which is the solution we have. This concentration is 1000 micromolar. So answer comes out to be 0.1 ml. It means you take 0.1 ml or of this solution which we have made here, and you diluted it to 100 ml. It will give us 1 micromolar. However, this 0.1 ml is very low volume as compared to the solution we are going to make. So you may get certain sort of errors by having this much difference. So it's better we first diluted it to some middle value, like we may dilute this 1 millimolar solution or 1000 micromolar solution to first to 100 micromolar and then dilute this 100 micromolar in the next step to 1 micromolar. Let us see how we are going to do this. Now, how you can dilute the 1000 micromolar solution to 100 micromolar? You can use the same formula C1V1 equals to C2V2. And by putting these values here, like our C2 is the 100 micromolar which we want to make, and V2 by set yourself you want to make 100 milliliters of this solution. So they come out here, and 1000 micromolar it goes down. It is the C1 concentration we have, and V1 we want to find out. So I also put the units here so that we can cancel out the units to get the correct units in the end. Like here, this micromolar will be cancelled out by this micromolar, and what is left is milliliters, and the answer is 10 ml. So 10 milliliters, if we dilute this 1000 micromolar by taking 10 milliliters of it to 100 ml, the solution we find is 100 micromolar. So 10 ml to 100 milliliters is quite a reasonable number. Now we can dilute this 100 micromolar solution which you have just made to 1 micromolar, and for this using the same formula by putting the values here, the answer comes out to be 1 milliliter. So it means if you dilute 1 milliliter of this 100 micromolar solution to 100 ml, it becomes 1 micromolar, and this 1 milliliter is quite reasonable as compared to 0.1 ml, which was very low volume and could have some errors. Here is just another example. You want to make 10 micromolar solution, 100 ml of glucose. So here again you have to make a concentrated solution, for example 1 millimolar, and by dissolving 18 milligram in 100 ml. So using the same formula, and the units should be the same on both sides, so you can put that here, and what you get here is 1 milliliter. It means you can dilute 1 milliliter of 1 millimolar solution to 100 ml by adding 99 ml water. And you also should make this in volumetric flask to avoid any errors. So you first take the fill it with water, and then you can add 1 ml and you can make final volume to 100 ml. So in this way you can make this solution. This is just another example of diluting the concentrated solution by using this C1V1 formula. Here I am taking the same example once again just to give you an example of conversion of different units. Like you can convert 1 millimolar to 1000 micromolar as I discussed earlier, but you may also convert other way around. You may convert this micromolar to millimolar rather than converting millimolar to micromolar. Like in C1V1 equals to C2V2. So in the last example we saw that you converted this C1 which is equal to 1 millimolar, and we converted it to the 1000 micromolar. But here we are not changing this. Rather than we are changing the C2. The C2 is 10 micromolar. So how to convert this 10 micromolar to millimolar to make the unit same on both ends? So rather than making this conversion, we are making this conversion. Here, whenever you want to find out or you want to make such kind of calculation, here is the example. Like 1000 micromolar contains 1 millimolar. These are the same. So, and you want to find out how many millimolars in 10 micromolar. So you just multiply this 10 micromolar multiplied by 1 millimolar divided by 1000 micromolar, and this micromolar cancels out with this micromolar, and what is left is millimolar, and this 10 divided by 1000 is 0.01. So it means 0.01 millimolar is the same as 10 micromolar. So this may, I just thought that this may be an helpful formula to convert these units from one to another. And now simply by putting in here in the C1V1 formula, rather than micromolar in the last example, I put it here millimolar, and you can find the answer is the same, because you dilute 1 ml of 1 millimolar solution to 100 ml, and you will get this 10 micromolar of the solution. Here I take example of one of the simple solutions is tricidity buffer. Although this is a simple buffer, but you can use the same information for more complicated solutions. And also the information I have just discussed earlier about molar concept and C1V1, that all will be used here. So for example, you want to make a buffer of 10 millimolar trischloride and 1 millimolar EDTA. So for this, because these are lower concentrations, so you first make the solutions of higher concentrations. So we call those as substock solutions, like 100 millimolar of trischloride and 100 millimolar of EDTA. But what you do is usually you actually make stock solutions of much higher concentrations, like in this example 1 molar trischloride and 0.5 molar EDTA. And these stock solutions are diluted to substock solutions, and that substock solution is diluted to the final concentrations. So many of these solutions you have to make on paper and just make the dilutions, which is quite easy, although you have to be careful. But for making these stock solutions, you have to be very careful how to make certain stock solution. So here I give you the example of preparation of two stock solutions, EDTA of 0.5 molar and trischloride of 1 molar. And from where you will get these recipes? You should get these recipes from some authentic protocol book, like the volumes by Sambrook in molecular biology, and similarly there are books for enzymology and other buffers that are available. So you should take the recipes from there. And also for buffers, you can make your own calculations using Henderson-Hasselbalch equation, etc. But it's better to get these values from some standard protocol book. So only try for yourself for making calculations for those buffers if you do not find such calculations from anywhere. But what you will get from those solution books is that how you are going to make it, like molecular weight of EDTA. Now it depends which EDTA salt you have, like you have 2 water molecules, 2 sodiums are attached. So it's, for example, its molecular weight is this one. So for 1 molar of EDTA, you need how much? You need this gram per liter. And for 0.5 molar, of course, you divided it by 2 and you need this one. So we are not going to make 1 liter of it, so you just need 100 ml of it. So you need only 18.61 gram of this sodium EDTA, and you dissolve it in lower volume, maybe in 60 to 70 ml. And for this, you use some use some beaker that is placed on a magnetic stirrer. As in this example, you can see this may not be EDTA, but just to give you an example, this is a magnetic stirrer and magnet inside, and you put 70 ml of water and you put this EDTA step by step. You do not add all of the 18 gram at once because uh, it, it may clog on one side. So you need to add one slowly. Now, another important point here is that you have to adjust the pH to 8 with 10 molar sodium hydroxide or NaOH pellets. So this solution won't be prepared at all unless you set the pH to 8. So it means along with this you also have to check the pH with the help of pH meter. So and this solution will become clear only when it will reach to a certain pH. Otherwise, no matter what you are trying to dissolve it, it won't dissolve. So, and finally, this is one of the volumetric flaws. When your pH is set and whole material is dissolved, you transfer this to a volumetric flask very carefully, and there is a mark on it, and you make the volume up to that mark. So it depends how much you want to make. If you want to make 100 ml, you use 100 ml volumetric flask. If you want to make 1 liter, you have to have 1 liter volumetric flask. Now similarly for triscaloride stock solution, you dissolve 12.1 gram of tris base in 70 ml. And because its molecular weight is 121 and you want to make it in 100 ml. And here too you have to adjust the pH. Now this time with concentrated HCl, and pH is also 8 in this case. And after dissolving in the similar way, setting the pH, you make the final volume to 100 ml for this as well. Now for any solution you can use this pattern of calculation and making the solution, that you first make the calculations, then dissolve in lower volume and check whether you need to maintain the pH or not. And if you want to maintain the pH, then you should do that and finally do the final volume, and you will get these stock solutions separately. You always have to make these solutions separately. If you have one solution in which 5 ingredients are there, you have to make 5 stock solutions separately, and then finally you can combine those. So here of course a lot more efforts are there, because you have to do this by following this procedure. But otherwise, for the substock solutions and for the final concentrations, there are some calculations followed by simple dilutions. Now here I discuss how you prepare substock solutions from the solutions you just made. Like you want to make 100 millimolar of triscaloride and 100 millimolar of EDTA substock solutions. And you will use the same formula of C1V1 equals to C2V2. And first you have to make the units same. So you have made triscaloride 1 molar, so you convert this molar into millimolar. You have this 1000 millimolar of triscaloride by converting these molar into millimolar. So now putting this in this formula, so V1 equal to, this is the C2 concentration you want to make, and this is the 100 ml, this volume you need, and divided by the concentration you have, as I mentioned earlier quite in detail. And you cancel out the units and do this mathematics. So volume is 10 ml. So you dilute 10 ml of this in the volumetric flask to 100 ml and to make this 100 millimolar. And similarly for EDTA, it is 0.5 molar. So to make the units same on both ends, you convert this to millimolar, so 500 millimolar. And putting in the same formula by the same way, by cancelling out the units and do the mathematics, so it is V1 equals to 20 ml. So you dilute this 20 ml of 0.5 molar EDTA to 100 ml in volumetric flask. It will give you the 100 millimolar EDTA. So now how to prepare final solution of tris EDTA buffer 10 millimolar trischloride, 1 millimolar EDTA, and if you want to make it 100 milliliters. From the substock solutions for trischloride, this is the C1V1 equals to C2V2 formula. 10 millimolar is the concentration you want to make, and 100 ml is the volume required, and 100 millimolar is the concentration you have. So by cancelling out the units and doing this simple mathematics, you come up with 10 ml. And similarly for EDTA, this is 1 millimolar is you want to make, and this is the volume you need, and this is you have, and here you get 1 milliliters. So it means if you mix 1 milliliters of 100 millimolar EDTA and 10 ml of 100 molar trischloride, and you make the final volume to 100 milliliter in volumetric flask, you will get this solution. And you can use the same pattern for any of the complicated solutions as well. Here I give another example. Sometimes you have to make such kind of solutions like how to make 500 milliliters of 0.25 molar solution of glucose. So first you have to calculate how much amount of glucose is required to make 0.25 molar glucose, because you know the molecular weight of glucose is 180. So for 1 molar you need 180 gram in 1000 ml. So you just multiply this 180 with the molar concentration you want to make. Like for 0.25, you just multiply this with 180, it comes out to be 45. It means if you dissolve 45 grams of glucose in 1000 milliliters of water, using the same pattern I discussed earlier, you get 0.25 molar. But if you want to make 500 milliliters, then you should use this unitary method, which is very simple one. Once again, you might remember it from your primary classes, that for 1000 milliliters we take 45 grams of glucose, and for 1 ml we would need 45 divided by 1000, and for 500 ml we would take 45 divided by 1000 multiplied by 500, and by using this simple formula it comes out to be 22.5 grams. So if you dissolve 22.5 gram glucose to final volume of 500 ml, it comes out to be 0.25 molar. And remember, when you are going to make this solution, you first you use the same pattern, like you just dissolve it lower volumes, maybe 400 milliliters, and adding stepwise. You weigh this at once and then start adding stepwise using the magnet and on the magnetic stirrer, and when it is dissolved you transfer to the volumetric flask to make this volume up to 500 milliliters. Another type of calculations are percentage solutions, like if you want to make 250 ml of 0.25% solution of glucose, how to make that? So for this you need to use this calculation using once again the unitary method, which is quite simple one. Like for 100 milliliters we have to take 0.25 grams based on this percentage, and for 1 ml we would need 0.25 divided by 100, and for 250 ml we just do this calculation 0.25 divided by 100 multiplied by 250, which comes out to be 0.625 grams. It means if you dissolve 0.625 grams in some volume, making the final volume to 250 ml, that will be this percent solution. Sometimes you have to make solutions like ppm or ppb, parts per million or parts per billion. So ppm is just milligram dissolved per liter, and ppb is microgram dissolved per liter. So I give you an example of making a solution of 1000 ppm of sodium using sodium chloride. So formula weight of salt sodium chloride is 58.44. Here we want to calculate the amount of sodium in sodium chloride, because we are interested in making 1000 ppm of sodium, not of sodium chloride. So 1 gram of sodium in relation to formula weight of salt is 58.44 divided by 23, because 23 is the formula weight of sodium. So this comes out to be 2.542 gram. So if we weigh out 2.542 gram sodium chloride and dissolve in 1 liter, it will give us 1000 ppm standard solution of sodium. And for 1 ppm, if you want to make it for 1 ppm of sodium, then it will be 2.542 milligram sodium chloride dissolved in 1 liter. So it is 1 ppm. Because here you have dissolved 2.542 grams of sodium chloride, it is 1000 ppm of the sodium. And here it is, because of this milligram, it is 1 ppm. Similarly, if you want to make this 1 ppm solution, it's better to make a concentrated one and then dilute it by using simple unitary method. And similarly, solutions in parts per billion range, they are also made by dilutions, because this microgram is very almost impossible to weigh out in routine labs, to weigh out in microgram amounts. So you need to make concentrated solutions, and then you have to dilute those solutions to the required volumes. Calculation of times dilution is also very important in many solutions. For example, if you have to dilute a 5 ml solution 3 times, so how would you do that? You simply use this formula for this purpose. So volume to be diluted into times dilution to be made equals to final volume. So in this example, you want to dilute 5 ml solution, and you want to dilute it 3 times. So what will be the final volume? So it comes out to be 5 into 3 equals to 15 ml. So it means make 5 ml solution to 15 ml by adding 10 ml solvent. It will be diluted 3 times. So similarly, you can use this formula for any times of dilution you want to do. Another example is how to find out the times dilution. Like if you dilute 250 ml of some solution to final volume of 950 ml, and you have to calculate how many times it is diluted. So for that purpose, you use the same formula actually. Volume to be diluted into times dilution to be made equals to final volume. So put these values here. Here we have the solution which is going to be diluted, 250 ml. And here you want to find out the times dilution. And final volume we already have here. So by putting in this here, so this 250 will go down here, simple mathematics. So 950 divided by 250. So these units are cancelled out, and you get this 3.8 times dilution. Meaning if you dilute 250 ml to final volume of 950 ml, you get 3.8 times dilution. I hope with this presentation you will be able to make solutions from simple to complicated ones by yourself by using these simple calculations. Thank you very much.